Okay, so welcome to everybody to this first seminar of this season of the Brussels Institute for Advanced Studies. It's very nice for you to be here. So it's very nice that you are here, and I'm very happy that we can restart another nice and interesting season. So a little bit of change with respect to the previous season is that we are having our seminars around lunch break in such a way that we can increase the participation from the various local research groups. And of course, as I said also last year, consider that the seminars are a moment to learn, but even more than that, are an excuse to then stay a little bit longer later to speak with people, to interact, and to create new connections. If you have crazy ideas, we love them. So let's go for it. So this said, today we have two very nice seminars. One from Antonella Ferrara, that is one of our senior fellows resident here for this month from the University of Pavia. And the other from a local, that is Rodolphe Sepulcre, that is now at KU11. So it's my pleasure to introduce our first seminar, that is Antonella. So Antonella Ferrara is a professor of the University of Pavia. She is a brilliant researcher with a lot of accomplishment in her career. And at the very same time, she is also a person extremely involved in our scientific communities. I think I lost track of the number of positions you held in the Control System Society and on the International Federation of Automatic Control. So I'll not even try to say the various things. One may be that it's particularly, for which you are particularly known, it's also your huge effort in women in control and in other similar activities to try to do outreach of our community within various specific groups. So it is really a pleasure for me to introduce Antonella, that will speak to us about traffic control.
Well, thank you very much, Emanuele, for a very kind introduction, and thank you, of course, for the invitation to spend this nice time here in BrIAS. I'm really enjoying my stay, and I hope that there will be also other occasions in the future to maintain this very nice connection that has been created during this time. Well, the choice of the topic is a bit in the direction of outreach, in the sense that normally when I'm invited to give a seminar, I prefer to talk about my theoretical work, which is mainly in the area of variable structure control, nonlinear control. But in this particular occasion, I thought that talking about something a bit more, let's say, open to possible, let's say, contribution from other discipline out of control could be better. And that's why I choose this topic. It's also a topic strictly connected with the theme of the program. So sustainability is one of the keywords of the BrIAS program this year. And so I thought that this could be interesting for the audience having something on this topic. I go immediately to the motivation. So the motivation is a bit straightforward, but maybe could be useful to review it. So we know that it's extremely important in our countries to have an efficient management of road traffic. And this is particularly true nowadays because during the last years, we have seen a significant growth in the number of vehicles on our road. So it's quite common to be, let's say, stuck in congestion, traffic congestions, and to lose and waste a lot of time in that situation. This is, for instance, a picture taken by my daughter when she was attending her bachelor program in Milano, and she had to commute from Pavia to Milano any day. Sometimes, of course, she tried to use the train as much as possible, but it was quite common, at least in Italy, it's common to have strikes, to have some, let's say, problem with the traffic system, with the train system, and so she had to use the car, and that was the situation. So 1 hour more or less spent any day to enter Milano from the outside area. But apart from this particular problem of wasting time, having this, let's say, non-wellness due to this kind of problem, there is also the problem of the road fatality, so the number of people which any year are killed because of irregular and intense traffic. If we look at the number, I just reported the data of 2023 because they are consolidated data, while the data of last year are still a bit, let's say, fuzzy. But if we look at the data in the European Union, I was really impressed by this. Any year there are more or less 20,000 people killed in road accident, and considering the trend that can be seen in these figures, it seems highly unlikely that many countries in the European Union will be able to meet the so-called objective for, let's say, 2030 of reducing by half the number of direct road fatalities. So we are in a situation which is not the best one, definitely, and we need to do something. And of course, coming to an aspect which is more related to the program of this year at BrIAS, we need also to consider the indirect road fatalities. So I just checked a bit of data which are produced by the World Health Organization, and in particular, it can be seen that road traffic is the second, in transportation system in general, but in particular road traffic, can be seen as the second major cause of fatalities due to pollution, the so-called silent killer. And so these were a kind of, let's say, element to keep in mind. And in particular, I'm a control engineer, and in this position, I tried to think what could be done, which kind of contribution a control engineer can give to this problem that I mentioned. And let me say that even if I started to work in traffic control more or less 30 years ago, so don't try to estimate my age from that element, but anyway, you can imagine that I'm a rather senior, but now it's the best moment to deal with traffic control, because in the past we had some problem with technology. Now we have the right technology to tackle the problems related to traffic. We have a new sensor, we have a new actuator, we have very much advanced communication technologies, and we can also exploit the potentialities which are offered by electric mobility, which was not so true in the past. And of course, as control engineers, we also have a very large portfolio of efficient, resource-aware control methodologies that can be customized to solve the problem of traffic control and reduce traffic congestion. And they can be easily deployed in the control rooms that you have in any major traffic networks, and they can help actually to make the traffic system, which is a kind of plant, a kind of process to control, make it more coordinated, more sustainable, this is a keyword, compatible with the goal of climate neutrality, which should be, let me say, an important element for any countries nowadays, should be, I use this verb. And of course, make also the traffic system safer. So this was the motivation, but just to be a bit in the direction of the outreach. So for those who are not experts of control, what does it mean to control a road traffic system? Well, a road traffic system can be seen as a plant, as I said before, as a process. For instance, in my university, I teach process control. A process can be, let's say, an electric motor, can be an air turbine, can be the kernel of a nuclear plant. So even a traffic system can be seen as a process to control, and this means that we can identify kind of actuators able to act on the system, kind of sensor able to acquire measurement from the system, and on the basis of those quantity, we are able to close a loop, so assume to have a certain reference signal which can be related to the good operation of the traffic system, so for instance, the density below a certain threshold, and then relying on the error between the reference and the actual measurement coming from the system, we can design a controller in order to make the system operate in the good way. Of course, it's a kind of system which is a bit complex and difficult to control. We normally use sometimes like nonlinear, large-scale, switched, hybrid, constraint. So it's a kind of system which is not, in general, easy to model and not easy to control, that's for sure. There is also the problem that I tried to put into evidence in the slide, that normally the system is large-scale and distributed geographically, which means that there are very long communication lines between the sensor and the control room, and between the control room and the actuators, which implies that there are a lot of problems like jitter, packet loss, noise, delay, so kind of things that our computer scientists are very happy to deal with. And as for the controller design, which is, let's say, more my task, I mean, the task of the control engineer, just to tell you what is the normal way to tackle this kind of operation or activity, it is normally, the controller is normally designed solving an optimization problem. This is the most classical way to do that. Normally we use an approach which is called model predictive control, so something which is the solution of an optimization problem relying on the model of the plant. And this, of course, solving an optimization problem means also to consider some other criticalities, which I listed on the slide. The fact that we need to keep an eye on the computational load. We needed to keep an eye on the computational efficiency. So let's say the computer science system, which is, or the computer science knowledge that is needed to implement this kind of system is not low level. Actually, it's very, very important. And the major issue is the fact that all the operation must occur real time in this very large scale, sparse system. So this is just a picture of the major difficulties that we have in this field. And if we look at the control objectives, there are some which are more traditional and some others which are, let's say, more recent. As for the traditional, definitely if you look at papers, let's say, of, let's say, 15 years ago, 20 years ago, you notice that the majority of the researchers focus on objectives like the total time spent by the vehicles in the system, or the total distance traveled by the vehicles in the system in a certain time interval. So they are kind of objectives which are more related, let's say, to the throughput. So having a system which has a high throughput and correctly exploit the capacity that the system has. Then there are also other kind of objectives which are more similar to the picture that I showed you before of the control scheme. So having a set point, or for instance for density, or having a set point for a speed, macroscopic speed of the traffic flow. So having a reference signal to track. This is important typically to try to exploit as much as possible the system capacity. And of course, there are the more modern objectives, the last one, which are more related to sustainability. And if you look at a recent paper on traffic control, many researchers, so let me say the majority of the researchers, focus on fuel consumptions. When I talk about fuel consumption, you must imagine the fuel consumption of the overall system, not of a single vehicle. All the vehicles present in the system in a certain time interval. And another aspect very important is emission. As I said, you remember pollution. So if we reduce the emissions, we can do some good for that particular aspect. And then there is noise reduction. Even noise is a form of pollution, and we must consider that when we control a traffic network. And of course, there is energy efficiency. This is particularly true considering the electric mobility. So in the future, we expect that the penetration rate of electric vehicle will become higher and higher. So keeping an eye, having attention in controlling the energy or optimizing the energy efficiency is an important action to take. And the other aspect that I want to mention is environmental risk mitigation. For instance, just reporting the experience in Italy. In Italy, it's quite common that goods and freights are transported using trucks, not so much using trains, but majorly using trucks. So very risky kind of goods are transported over the normal traffic networks that we have, with a huge environmental risk, because if there is an accident, there is a risk for the people, there is a risk for the environment. So all the areas which are close to the road where a very risky good is transported, along which the good is transported, is running a risk, even without knowing that. So it's important to consider. So just to summarize the major topics that I'm going to mention in the remainder of the talk. So I will start from the classic method. I was talking before with some of the students, and I told them I will try to start from the elementary aspect to make everybody able to follow. And then I will describe some recent development, in particular based on the modeling of service stations with recharge facilities, which are very important when you have an increase in penetration of electric vehicles. Then I will move to the major, let's say, theoretical part. So in that part, we did some good, at least in my opinion, of course, personal opinion, research work, and we provide a very nice result. So it's the multi-scale traffic modeling and control perspective. And of course, I will also make some short example to relate especially to sustainability objectives. So I start from the classic methods, and this can be useful as a sort of overview of this field. The first thing to be said is that traffic control methods are model-based. So they need a model. Now, it's quite in fashion to talk about data-driven control. And of course, I could give a second seminar on data-driven control of traffic system. But as I said, I prefer to start from the very basic topics. And so in classic traffic control, we use models. The models are typically models describing the traffic flow as a fluid, and I will tell you something about that in a moment. But the very important feature that I like to underline is that the models used in traffic control, so to design traffic control algorithms, are typically models capturing a single scale. So we have macroscopic models, so the fluid vision that I said before. Then we have mesoscopic models, which means models in which also some phenomena like car following, car overtaking are included in the model. And then we have the microscopic model. So any single vehicle present in the fluid is described mathematically, explicitly in the model. In this presentation, I will focus on freeway traffic control. There is another chapter which is urban traffic control. And of course, there is also another chapter in which the two kinds of traffic are connected. And so design or control is done assuming to have the different possible types of traffic. But let me say that freeway traffic control is, in my opinion, better as a topic to start with if you want to start doing some research in this field. It's very educational, in my opinion. And since I focus on traffic control in freeways, I start focusing on macroscopic models because they are those traditionally used to design control for freeway networks. If we start from the very, very beginning, I don't know if you can see because I wrote a bit small, but if you look, the date is 1956. So one of the first models which was proposed and became extremely, let's say, used everywhere in the world is the so-called Lighthill, Widham, and Richard model, which is, or LWR model, which is just based on a macroscopic description of the traffic flow by means of this PDE that you see here, so partial differential equation, in which there are two variables, which are the important variables, rho, which is the traffic density, so the density of the macroscopic flow, macroscopic traffic, and F, which is the flow itself, which is assumed to be related to density by means of this rather famous diagram, which is called traffic fundamental diagram. The traffic fundamental diagram is a steady state relationship between flow and density. And it's very typical considering a specific traffic network. So for any network, you could assume that for any portion of the network, you have a specific fundamental diagram. So it strongly depends on the morphology of the road and on the type of traffic you have on the road. That's the first thing to be said. Second model, which is very important, which was proposed in the 19th, so more or less 40 years, let's say 30 years later, the first one, is the called cell transmission model. Here the idea is the following. You have a freeway stretch, so imagine a stretch of the road, and it is subdivided into cells, and for any cell, we use a single equation. Here it is, you see, a discretized version of the equation, discretized in time and space. So a single equation to describe density. So this is the only state variable, we call it in the control context, to describe the dynamics of that particular cell. And then at the interface between two cells, you see that there is this variable F, the traffic flow, which is computed relying on a very classical mechanism, which is called demand-supply mechanism. So the idea is the following. The flow moving from one cell to the other is computed as the minimum between the so-called demand, so the flow of vehicle that ask to enter in the next cell, and the supply, which is the flow which can be actually accommodated by the subsequent cell. So it's a very simple model, and it can be seen as a discretized version in space and time of the LWR model. So we are just using a state variable, delta, the density, so here indicated with rho. And this problem is very widely used, but, or very, let's say, massively used in many research groups dealing with traffic control, but it has a problem that must be mentioned. It is not able to capture a phenomenon that we have in real traffic system, which is called capacity drop. What is the capacity drop? Let's look at this picture in which you see a typical natural bottleneck. So you have a road with a certain number of lanes, and then there is a restriction. So the number of lanes in the subsequent part of the road is lower. If this wider part of the road is congested, then when the vehicle enters this point, so which is the actual bottleneck, they have to increase their velocity to move from a low velocity normally associated with a congested portion to arrive to the so-called free velocity of the uncongested part. So there is the need to describe the acceleration to capture this phenomenon. But if we don't model velocity, we don't model the dynamics of velocity, or speed, it's impossible to capture a phenomenon related to acceleration. So using the CTM, we can only model the dynamics of density, but we are not able to describe this phenomenon. Some variation have been done. I just mentioned one variation to the characteristic of demand and supply, which are the typical ones used in traffic control. And I also wrote some papers on this, so how to extend the cell transmission model to capture the capacity drop. But let me say that, honestly, the best thing to do is to move to a second-order model. So a model in which, for any cell, instead of describing only the dynamics of density of traffic, you also describe the dynamics of speed. So if you see here again, we have a cell of a certain length, we have a first equation which is just describing how density evolves in time, and we have a second equation which describes how speed evolves in time. And in this way, it can be demonstrated that the capacity drop is naturally encompassed in the model, which is a very, very nice thing. So the MetaNet model, which is the name of this model, was introduced by Papageorgiou in more or less in the same time of the CTM, so immediately after. It is again another model which is very much used to design traffic control systems. But now let's see how traffic control has been realized, implemented in the past, and still now, let me say. There are many examples of application, real-world application of traffic control that sometimes we don't even realize that they are operating. For instance, in the Netherlands, it's quite, you see, this picture is was donated to me by a body managing traffic networks in the Netherlands. So they apply already traditional control. There are many examples in France, many examples in Australia, not many examples, or let me say 0 example in Italy, because in Italy we have some kind of policy for which it seems impossible to apply this kind of algorithm. But let me say that I hope that something will change in the future. So, which is the major feature of classic traffic control? It is infrastructure-based. What is the meaning of infrastructure-based? You need some physical device present on the road, so present in the infrastructure, to implement the control action. So I just mentioned ramp metering, so the first kind of technique, which is a kind of regulation of the flow of vehicle asking to enter the freeway from the on-ramps. In that case, you can implement a ramp metering strategy by means of traffic lights, so just delaying the vehicles entering. And then there is the so-called mainstream control. Mainstream control needs variable message sign. So it's a speed control in which instead of having, let's say, kind of speed signals which remain constant in time, you adjust the speed limit considering the state of the traffic system, so the condition in which the traffic system operates. And then there is the so-called dynamic routing. In that case, what is done normally to alleviate traffic congestion is to propose a different direction, different route for a special category of vehicles, typically trucks, vans, heavy-duty vehicles. And in all cases, you need some kind of variable message signs. So you see, you need a piece of infrastructure to implement the action. Very recently, we proposed some development in that particular area of traffic control, so the infrastructure-based one, and we propose in particular to extend the classical models to include the dynamics of service stations, in particular service station with equipment for vehicle recharging, for battery recharging. The idea is that vehicle may stop or may be induced to stop in the service station, and this may be used as a way to alleviate the congestion in the main stream. Of course, to do that, we need to make the infrastructure, the service station become a sort of active traffic control element. So we need to incorporate some variable pertaining to the service station in the control problem and determine how those structure must be, let's say, set, which is the correct setting. But in particular, what can be done is to extend the models that we have seen before to incorporate the dynamics of the service station. For instance, we did that for the CTM and we call it the CTM-S. We did that with the MetaNet and we call it the MetaNet-S. And having a more extended model, so incorporating even what happens inside the service station or what may happen inside the service station, we were able to solve different type of control problems, but in particular to solve control problems related to traffic in a different way. So in particular, a very simple idea that could come to anyone is just that of applying ramp metering at the exit of the service station. So to delay a bit the remerging of the vehicle who stayed in the service station for a while into the mainstream. And this can be beneficial for reducing the density in the mainstream. A second opportunity is that of using game theory. So the problem in this case is very much, let's say, appropriate to be formulated as a game in which there are different players, and they have to reach some sort of global optimum or a global benefit without, let's say, having regret. I tell you in a simple way, but this is a bit the philosophy. So, for instance, it's very nice to formulate the game theory problem assuming to use kind of incentives, so a reward. For instance, you can decide to let's say, reduce the cost of fuel in the service station for those taking part to that kind of game, or maybe you can offer a free coffee. In Italy, this could be very, very effective as a policy to, let's say, induce people to stop there and stay there for a while. In that way, they are collaborating to obtain a global optimum, global benefit for the traffic system on the whole. And so, in this case, as I said, the payoff could be associated with the current and future traffic conditions. So you need a model. So it's a game in which you need to consider the model. So it's a model-based game problem. And then, of course, in this case, you could, for instance, use the outcome of the game to define the flow entering the station, or, as I said, the time that the vehicles have to spend in the station, in the service station. And the very final application that we have considered using service station dynamics explicitly model is to use the model not after that the service station is built, but a priori. Because if we can optimally locate the service station in the traffic network, we can increase what for the control engineer is a very well-known term, controllability of the system. But in a simpler term, it means we can increase the effectiveness that the service station as an active control element can have. So that's the idea. So use the models to build new infrastructure, to build new service stations, making them actually effective in this perspective that I just tried to describe. And now I move to the new trends. The new trends, as I said, rather recent, let's say less than 10 years right now, is that of exploiting the so-called heterogeneity on the road and to try to incorporate in our control problems the natural multi-scale property that a traffic system has. I try to describe what I mean in the following. So first of all, we have to consider that in recent years, a lot of, let's say, advancement have been acquired or obtained in the field of intelligent transportation systems. This means that we can consider some kind of vehicles which are a bit special with respect to the other normal vehicles that we have in our system, that normally we call them CAV, so connected and automated vehicles. I must say that in some works that you can find in the literature, people use the term connected and autonomous vehicle. I don't like that. We don't need to do something which could be applied in 50 years. Now we need to do something at the moment. So that's what we need to do. So something with the technology which is now available. That's why I don't use autonomous vehicle, I use automated vehicle. Because from my point of view, all the strategies that we have proposed can be easily implemented using very, let's say, commercial technology that is now available on vehicles. For instance, let's say a classical adaptive cruise control, traction control, ABS. So sometimes we simply need to inject in the vehicle ECU, electronic control unit, a reference for the vehicle speed. And then if you have an adaptive cruise control, everything works. So you don't need that the vehicle is autonomous. The driver can be on board. And of course, this could be an element which makes the research a bit more complex. Because something that I would like to do in the future, and I'm not doing it now, is to incorporate also a model of the driver behavior. And this could be a very nice enrichment of the model that we are using. So, of course, we need that the vehicles, so these connected and automated vehicles, are connected in the sense we need that they communicate. So they need to communicate with the infrastructure to receive some signal and to send possibly some signal if they have information that could be nice to share. But they also need to collaborate and then communicate with the other connected and automated vehicles. This increases the traffic heterogeneity, because if we look at the macroscopic traffic, actually we can observe in this particular system different types of elements. So there is the set of the conventional vehicles, and then there is the set of the connected and automated vehicle, which can be further subdivided into subsets. You may have the connected and automated vehicle, which are, let's say, use, let's say, an endothermic motor, but there can also be the electric vehicle, which are connected and automated, and then you can also have public transportation means like buses and electric buses. So we have a lot of different agents, let me use this technical term, with different natures and different dynamics that can cooperate to provide a sort of solution to the control problem that we mentioned. So this heterogeneity is the element that is now exploited to have more degrees of freedom to design traffic control system. And that's the novelty that we have. Of course, one has to understand in which way I can control connected and automated vehicle to influence the macroscopic system. The idea is to control them individually or to control them generate information. But in particular, the basic idea is that of create a sort of artificial bottlenecks that are moving along the road. So they are not fixed. They are not like the natural bottlenecks, which typically are in a position and they remain, apart from accidents, which are there in a position and remain for a certain interval. But if you have a free lane, one lane, free lane, two lanes, there are kind of bottlenecks that where they are, they will stay forever, unless the road is changed. Now we try to create bottlenecks moving along the flow. And you should imagine this kind of element, like kind of atoms or individual elements which are immersed in a macroscopic fluid. So if you have an expertise in fluid dynamics, you can understand what I mean. So you have particles which are distinguishable, so they can be distinguished, but they are immersed in a macroscopic fluid. So in some sense, they are constraints. They cannot do everything they want. And well, one question could arise, but is it really possible to control a fluid, a flow of vehicles just operating on some sparse element in this fluid? Well, we have a demonstration, so we don't have a theoretical proof, but at least we have a demonstration of the fact that even in practice, some good results can be found. And in particular, I don't know if you heard about this experiment. There was a massive experiment a few years ago in 2022 in Nashville. And so a nice group of people, I mean, they are all colleagues with whom I have a collaboration. They are mainly from Berkeley and other university in the States. And the project that they were, let's say, involved in is called Circles. But in particular, the final, let's say, the showcase was to deploy 100 connected and automated vehicles on a Nashville interstate in the commuting time, so early in the morning, and then observe. These vehicles, of course, were controlled in the sense that reference speed were sent to the vehicles, and to observe what happened. And the result was very, very interesting. So there were good results. The traffic flow was definitely regularized by injecting those particular vehicles, having a very regular behavior in the macroscopic flow. So we have some example, or at least one major case of possibility of getting a result. But now I want to conclude, so go towards the last part of the seminar, just telling you how to control traffic, macroscopic traffic, by controlling curve and putting into evidence the multi-scale nature of the system that I mentioned before. One possibility, as I already mentioned, is to control the connected and automated vehicle as if they were a sort of macroscopic class of vehicles. So in this case, we have a system which can be seen as a multi-class system, but the scale is still macroscopic. Another possibility is to control them individually. I mean, control engineers say to apply a decentralized control approach. In this case, this can be done. We must be careful about the fact that if we don't introduce a bit of coordination, the risk that each vehicle is just following or trying to reach some selfish objective can be present. So you need to obtain a kind of good for the single vehicle, but in particular, a good for the entire system. That's something important. And the other so coordination is important. Another possibility is to create formation, as I mentioned before, to enforce even a bit more the energy that the single moving bottleneck can produce on the system, the impact. Again, I can control the platoons, so assume that a formation is a platoon, but actually there are also possibility of creating formation which have a form different from a platoon, kind of flock. Well, but let's focus on the platoon, which is a bit easier to consider. So we can again use centralized approach or decentralized approach, but again, a bit of coordination in this kind of system is always needed. But the element that I want to underline is that depending on the type of approach that you decide to use, you need a different modeling framework. And the point is exactly that. As I said, if you assume that the group or the set of connected automated vehicle is modeled as a macroscopic graph, you need a macroscopic model. So you have just a single scale with two different classes, but it's just a multi-class macroscopic model. But in the other two cases, so when you control individually the agents which are immersed in the macroscopic fluid, or you control them creating a kind of formation like the platoons, you need a multi-scale. You need to put into evidence the multi-scale nature of the overall system. That's important. And this actually offers a lot of new perspective for the research in traffic control. I mean, this is the concept which emerged in the last, let's say, less than 10 years, as I said, and has completely changed the landscape in traffic control. The idea is very simple. This is just, let's say, to give a kind of illustration of the idea. So let's assume that we have a traffic system. I try to put some, let's say, a symbol of a communication device just to say that some of them are actually connected and automated vehicle. Let's assume to have a demand. Consider that the traffic demand is something normally unknown. We can estimate it on the basis of historical data, but we have a problem with traffic demand. So typically we cannot predict it very well in some cases, but it's, let's say, a crucial aspect to consider. And normally what is known is the control objective. So think of, let's say, optimizing the energy efficiency of the entire system, reduce the fuel consumption of the entire system in a certain time interval. And then what we can do is apply the standard approach, which is that of solving an optimization problem, relying on a model which can predict with all the, let's say, approximation that are in order, the future development of the system. So in a classical approach, as I said, the model just predicts a single scale, typically macroscopic scale evolution. Here the idea is the following. We need to capture in the prediction model the macroscopic model, because of course this is important, this is the entire system, but if we want to control the platoon in such a way that they have an impact on the overall traffic dynamics, we need also to model explicitly the mesoscopic effects that exist in a platoon formation operation. And then, if we want to control the vehicle such that the platoon is maintained, is formed and maintained, we need to explicitly model the dynamics of the single vehicle. And then what can be said, if we have a model, we capture the different scale, then we can consider the model as a multi-scale model. This is the first feature to underline. But apart from that, we can explicitly exploit the different scale in the feedback. So generate a control which takes advantage of the different scale that the feedback encompasses in this particular setting and formulation of the problem. So that was the complete novelty of the last few years. This, let's say, this vision is rather new, but it was it demonstrated to be extremely effective. I just show you some example, try to go a bit fast towards at the end. A first example is that of electric buses which are immersed in a freeway traffic. Well, the idea is to consider electric buses in a freeway traffic setting, because normally in urban setting you have dedicated lanes. In many countries, at least this is true, I think also in Brussels. So you have dedicated lanes for the buses. And so in urban scenario, it's not so effective to control them. But if you think of buses that connect different towns, in Italy there are many, so they are inter-cities traffic, let's say buses lines, or in UK it's quite common to use buses to move, let's say, from London to Glasgow. It happened at least to me very often in the past. And of course, in that case you don't have dedicated lane, so the fact of having traffic congestion may affect the bus, and the bus could be controlled to affect the traffic congestion and try to alleviate it. Of course, we need to keep in mind two aspects. That we need energy efficiency, so because we don't want to waste energy, and on the other side, we also need to consider time schedule compliance, because of course the passenger cannot be affected by the fact that we slow down the bus in order to slow down the overall traffic. That's the idea. But doing that, you can formulate a problem in which you can control the buses immersed in the traffic with the objectives that we mentioned, so that of having the optimal values for the stopping time. During the stopping time, they also have the recharging of the battery, and so we also want to optimize the battery recharging. And to do this, we need a multi-scale model, because we need to describe the macroscopic traffic with the buses included, and then we needed to describe individually the buses, because we needed their position to know where they are in any moment in the traffic networks. And then, of course, we need also to explicitly model the state of charge of the battery to understand if it is actually needed to recharge or not. And so include this variable in the control problem formulation. And this is just an example of what has been obtained. So this is the signal produced by the controller. So you see that it's a reference for the speed of the bus. The bus is the red rectangle. This is IMSUM, a very common commercial software to simulate traffic system. Is a micro simulator, so any single vehicle is modeled explicitly. So you see the controller generates a reference for the speed, and then if you look at the flat area, it's a reference for the stopping time. So the bus received a knowledge, an information about the time that had to spend in any stop and any recharging station. And that's an example. It's applied to a road which is in Liguria. Liguria is the region where Genova is, and Genova is the town where I was born. And this is an application which has been very, very, let's say, appreciated by the traffic manager of Savona, which is another town. And the second example that I want to mention is a different kind of model that can be proposed to consider the different scale, still remaining connected with the classical model, but introducing some novelty. In particular, these models are based on the coupling between PD, so partial differential equation, and ordinary differential equation. And in this way, we manage actually to do what I said before, consider explicitly in the control the different scales. Just consider the first case I mentioned, that of having individual vehicles which are connected and automated, so they can be used as a kind of actuators in to control the overall flow. So don't forget that we don't want to obtain a result for the connected and automated vehicle. We want to obtain a result for the entire macroscopic system. That's the point, just controlling some sparse element in the flow. So the model is done in this way. You have a first part which captures the macroscopic part, so it's just the LWR model, so vehicle conservation equation. And then we have a constraint which is pointwise in correspondence, so a constraint for any connected and automated vehicle, which is a constraint on the flow. So we have a PDE with a constraint which is pointwise, which moves in time along the road, which introduce a bit of mathematical difficulty in dealing with this system. And then, of course, we need to have also an explicit ODE telling us for any curve, for any connected and automated vehicle, the position in time of this kind of vehicle. And well, this is a model which has been extremely effective in allowing us to propose a very new and very efficient kind of control schemes, which are different considering the number of scales that we want to actually put into evidence. For instance, having a two-scale example, we can assume to control all the vehicles individually using a centralized control approach, or in a separate way, in a decentralized way, but with a bit of supervision, as I said before. And in this case, we have just two scales. In this case, we have the macroscopic and the macroscopic and microscopic scale. And if you have a doubt about the fact that two scales actually influence each other, just look at this diagram. The first diagram, so this diagram is the speed of a single connected and automated vehicle, which you see, it's a triangle if you don't have any other constraints. But if you have the flow, macroscopic flow, the speed of a single vehicle cannot be sometimes equal to the maximum possible value. So there is a constraint imposed by the vehicles which are in front. So the macroscopic flow puts a constraint on the maximum speed. And on the other end, this is what I said before, the single connected and automated vehicle can create a reduction, pointwise reduction of the flow. So there is a jump. The flow jumps in a point which is moving in time. And this is something that actually show what is the nature of the system that we wanted to capture. Of course, as for the control design, just to repeat what I said before, we can assume that the high-level controller, which is the one solving the overall optimization problem, produce a reference for the speed of any individual connected and automated vehicle. And then the low-level control, so the one operating at the microscopic level, the one implemented in the ECU of any single vehicle, make the vehicle operate in such a way to track the reference produced by the high-level control. And this produces exactly the regularizing effect that I mentioned before, which I like to call, to give an idea, the safety car effect. The effect that is produced is very similar to the safety car effect in racing. So when you have a car that imposes, in practice, a slowdown to the entire system, and this can be beneficial to try to discharge some congestion, which is, let's say, downstreams. Of course, one could comment, well, of course, this depends on the number of agents that you have in the traffic flow. It's correct. So it depends on the penetration rate of connected and automated vehicle. If you look at the open loop case in which you have, this is a classic diagram that we use in traffic control. This is time, this is the number of cells, and what you see in red is a congestion, while in blue it's free traffic. So you see that if you have, for instance, an accident in this cell number 7, we have a, let's say, back propagation of the congestion in time and in space. And if we have different penetration rates of connecting an automated vehicle, we can have different effects in terms of control. So if we start from low penetration rate, 1%, 3%, 5%, 6%, 8%, so you see that the effect is improving, arriving more or less at 10, 12%. And then if you go beyond, you notice that more or less there can be a saturation. Of course, it depends on the morphology of the system, but the fact that typically there is a connection with the penetration rate is something that holds in general. And of course, you can decide to use more scales to solve the same problem. An idea could be that instead of using the single vehicle individually, to consider cluster of them that cooperate, so using a kind of distributed control inside the cluster. And in this case, you add a scale level in the sense that a scale element, in the sense that you have the microscopic scale of the vehicle, the macroscopic scale of the overall traffic, but also the mesoscopic phenomenon which are included or involved in the cluster generation. Even in this case, for instance, considering a road of 50 kilometers, 3 lanes, 1 hour of simulation, a very low penetration rate, 1%. You may ask why I use so low penetration rate. Because I want something realistic. I don't want to say, sometimes I see some paper with 80% penetration rate. But when we will be able to have 80% of penetration rate? 1% is reasonable. It can be applied now. And so you see that even in this case, if you look at this diagram where this is time, this is space, and the red part is the congested part, you see that using a certain number of connected and automated vehicles, the characteristic associated with each of them is the black line, you see that the red part is definitely reduced. Even as for this reduction, it's quite utopistic to expect a reduction of the 50%, of the 60%. A reduction of a low percentage is something normally correct and, let's say, very much appreciated. And the other extension that can be done is, as I said, to consider platoons. If we consider platoons, the model can be slightly changed. Again, we have the macroscopic level. We have the OD describing the position of the upper front and, let's say, upstream and downstream front of the platoon. And then we can also include a differential equation, ordinary differential equation, describing the length of the platoon. So in this case, again, we have some effect on the macroscopic traffic, and we have in this case a kind of moving bottleneck, so a moving capacity reduction, which is not point-wise, but in all the time interval, space interval, which moves in time, of course. Where the vehicles of the platoon are present, you have a reduction of the flow, so a kind of moving bottleneck, which is a bit more effective. Just for the mathematician, if there are mathematicians in the audience, consider that now again we have a jump in the flow, which occurs when the front of the platoon and the last point of the platoon passes, they pass in some particular position along the road. And this, so you see in this picture. So in this case, just to give an input to the mathematician, but I don't want to enter too much into details, the Riemann problem, which is underlying the solution of this, I mean, the overall control problem is a bit non-typical, let me say, and so some particular theory for shock waves, non-traditional shock waves is needed to consider this. And so this can be interesting. But coming back to control, which is, I mean, my field more than pure mathematics itself, I just want to mention that in this case, we are adding a new variable to control the system. So before, with the individual vehicles, we just controlled the speed, but now we can control the speed of any platoon, but also the length. And so we have two control variables which become relevant. And just to mention, to conclude, I'm at the very last slides, to conclude with an example of a problem with sustainability-related objective. If we apply a model predictive control in which the prediction model is the multi-scale model, including platoons that I've just mentioned, and we want to minimize the total fuel consumption. Here in particular, if you check the paper where more details can be found, the total fuel consumption that you find in the literature is very often related to speed. We added to customize it and redefine it in terms of density, but formulating the problem like that with some constraints on the maximum and minimum length of the platoon, some constraints on the maximum speed of the platoon, it was easy to solve, reasonably easy to solve a problem which is quite important, especially for my area, Pavia, where I live, is not far from Milano, and this is exactly the ring road around Milano is called Tangenziale di Milano, which is a traffic system normally congested. So I never saw it uncongested. That's at least if you go at night, maybe, but let's say late night. And in that case, if you try to solve the problem of considering 1 hour, minimizing the total fuel consumption of all the vehicles that were on typical volume of vehicles that are present in 1 hour in that system, this is the result that we got. This is the speed of the front part and part of the platoon, so which is varied in time by the controller. And the total fuel consumption with respect to the uncontrolled case was 2.6%, which, as I said before, may appear to be a small percentage, small gain, but actually, if you look at the number of liters of fuel which have been, let's say, saved with that control, with the action of the control, it was around 700 liters. And if you consider that any liter of unleaded petrol produces 2.3 kilos of carbon dioxide, at the end of 1 hour, with this very mild control, I didn't mention, but the penetration rate was 1%, we got a reduction of the emission equal to that of the emission of a flight from London to Los Angeles. So you can consider the volume of vehicle that we had in that road. So you can imagine which kind of benefit we could have if some simple controller, let's say, not so impactful, that's my point in terms of infrastructure elements can be obtained. And this is all I wanted to tell you to now. So I gave you a brief review of the classical method. I just mentioned let's say, the recent result on infrastructure-based control incorporating service station, but in particular, my focus was on the multi-scale control that you can apply in this application field. And of course, these new techniques, new control approaches can be mixed with the classical ones, obtaining very nice result. And well, this is some references for you. Credits, of course, to my co-authors. You see, the list is very long. Just put in random order because I was not able to organize it better. I just wrote them thinking of all the people I'm working with at the moment on traffic control and I worked with in the past. For the students who like to do something in this field or maybe study something, I suggest, well, I wrote a book with some two colleagues of mine, Simona Saccone and Silvia Siri, a few years ago for Springer. It's quite complete. There is a survey in Automatica, which is again a good starting reading for students, and a review in annual reviews in control, which is focused on sustainability objectives in traffic systems. And so maybe I think that this can be a good list of references. And that's all. Thank you so much for your attention. I hope to have captured your attention, but it seems that I did. Thank you so much.
So thank you, Antonella. I'm quite happy because, okay, I see that I have to move on the other side. So thank you, Antonella, for the nice presentation. I'm happy because I've learned something new, so that's exactly the goal. I imagine there will be some question from the public. Just a disclaimer, no jokes about the ring and the E40 are allowed.
Thank you very much for the talk. Maybe a short advertisement for the circle experiments that you mentioned. So the next issue of the Control Systems magazine is entirely devoted to that experiment. So there will be 5 articles on this topic. It's indeed one of the rare examples of a large-scale experiment that was run.
Exactly. Very, very, let's say, even expensive. So there was a large investment of funds to make it feasible. and a lot of dedication of the people involved, because I know that all my colleagues, our colleagues who were involved, spent hours on that road to prepare everything, to have on the experimental day, on the showcase day, everything working, and so it was really a massive effort, not only in terms of funds, but also of personal effort of the people involved.
So check out your magazine, it's just in a few days.
Yeah.
But my question perhaps is, okay, you present a control perspective, I would say,
Yes.
on traffic control. I imagine that the talk by someone from an AI perspective would be somewhat different. Can you comment on whether
Yes.
there is a sort of alignment more and more so, or on the opposite, whether there is a sort of a...
Well, you see, I started from the model base for the reason that I mentioned at the beginning, so it's the more classical, much more classical approach. At the moment, I must say that more or less everybody working in control is moving towards the data-driven, so AI-based, let's say, direction. I'm also doing something on that. There are colleagues in Berkeley who already published something on that. Let me say, in this case, there is a bit a problem that must be mentioned, the availability of data. So unfortunately, it depends a bit on the country, but I must say that having the access to the historical data is sometimes even a problem. Collecting a sufficient amount of data online could be a problem. So I think that the transfer the complete change of direction, in my opinion, won't occur in a few years. But it could become more and more likely to go towards that new, let's say, modern direction, if you want to use this term, if we learn to, let's say, produce data which are maybe not, they may be also artificial in some sense, so to complement the real data that we can get, with some artificial data which are reliable. So that's the point. So I see that, in my opinion, what must be done now, and this maybe is not an effort for control people like us, but maybe for people working in other disciplines, that of complementing the real data that we can collect with some synthetic data which have some guarantee of being reliable. That's the point. Maybe it's not only the problem of traffic control, it's a bit a problem in general. For instance, I also work in other fields like robotic rehabilitation. Even in that field, we are using artificial intelligence, but sometimes to produce good artificial data to complement the small amount of data that can normally collected from patients is the problem at the moment. So I think we don't have a problem in using AI algorithms, because many of them are already very, very much efficient. Of course, maybe I'm saying something a bit too extreme, but let's say an optimization problem can be sometimes, in the majority of the cases, reformulated as a problem where you can, for instance, use deep learning, deeper reinforcement learning. So very often you can, let's say, associate this idea of the optimum to the reward. But in my opinion, so my experience is that to use that kind of algorithm, you need data. And the other aspect is to be able to formulate the approach in such a way that you don't need much computational effort online, and you can do a lot of pre-processing offline. Because now, so unless new infrastructure will be implemented in the future, with the current level of computational power that is present in the field implementation that we have now, there is a lot of limitation. So we cannot make a lot of operation online. There is always the problem of, let's say, separating what can be done offline and online, because online you can do typically a small amount of operation, even assuming to have a sampling time which are not too short. So that's the two major problems, in my opinion, are those: data and computational power for the real-time implementation. That's at least this is my experience, which of course it's could be limited anyway.
So there is there is another question.
Yes, thank you for the nice presentation. I really enjoyed. My question is about the CAV or CAV-based approach for the controlling the actually stream of the vehicles. So the question is, because mostly the human-driven cars actually pay attention to the variable speed limits or infrastructure-based, and if this CAV cars actually suddenly decrease the speed, it might also affect the safety of the vehicles which are actually preceding the cars or following the cars. Have you also studied the effects of this approach on the safety and some metrics like time to collisions or the distance between the following vehicles? Or do you think that it might affect
I hope to have captured everything you said, but let me say that the reason why I don't want to talk about autonomous vehicle is exactly that of leaving to the driver the responsibility to avoid the collisions. So consider that in all this kind of control, particularly, let's say, the mainstream control based on speed limit that you mentioned, and the control of connected and automated vehicles are kind of, let's say, suggested control. So I suggest a certain speed, and then, as I said, if you think of speed signals, the driver has to accept that suggestion and implement it. For the connected and automated vehicle, it could be implemented in a more, let's say, strong way, imposing that this limit is the one, I mean, the new limit is the one which is received by the cruise control and then actually put into practice by the control system on board. But the other possibility could be just to send a message to the driver. So assuming that you have your navigating system on board and you see that in a certain moment the speed, instead of being that you see on the traffic sign is on the road, is a different speed, typically lower, because this can produce a benefit. So that part, the fact of avoiding collision is a bit something that need to be further explored. We are working on that, honestly. I am not saying that we are not working. Consider that at the moment we are also working on what is called a free lane control. So kind of flow of vehicles without lanes. So in that case, you can also, let's say, steer and change position, not only longitudinally, but also in a transversal sense. So, and in that case, of course, collision becomes a major element. Now, the idea is that the collision avoidance along one lane is a responsibility of the driver. In some sense, having the autonomous vehicle is even easier because you can implement some other, let's say, you can implement explicitly a collision avoidance strategy. But in my opinion, working only on, so having the driver sometimes can be even more difficult. Explicitly, if you want to take into account the behavior of the driver. So I didn't add many details, but of course you can enrich the model, also consider a model of the driver behavior, for instance, and in that case things becomes slightly different, but having the driver is actually adding complexity, so is adding the human factor, the decision capability that the driver has. And this kind of collision avoidance aspect could be encompassed in the control or let to the driver as it is normally done in normally driven vehicles. I don't know if I replied to your question, but...
Yes, thank you very much.
My pleasure.
We have time for a last fast question from Frank.
Thank you, Antonella. A very fast question, different field. How can you reconcile your control methods with personal privacy?
With this, sorry?
Personal privacy.
Personal privacy. Oh, yes, this is a, let's say, very serious problem. Of course, you know, any time that let me say differently. These kind of vehicles are considered as a kind of participants to a sort of collective game. So you should imagine a bit the situation like that. No? If I'm a driver and I am a vehicle which is equipped with the correct technology, I could be asked to take part to this collective effort to reduce traffic congestion or to improve the throughput of the system. So in that moment, you should ask a sort of, let's say, written agreement, and of course, the privacy aspect should be taken care during the typically anonymization effort that is done when you share data among different entities in a public scenario. So I think that is not a real problem, but of course we need consensus, so kind of written consensus, like when you go to hospital and you leave the physician take care of you. So I think that putting things in these ways, you agree to take part to this. And this could provide some direct or indirect benefit. So the fact that direct could be, as I said, maybe one could implement a policy for each. If you accept, you pay a lower toll to use the freeway, but the indirect could be, if you accept, you are contributing to making the system operate better, and so it takes less time also to you to reach your destination. So that could be the idea.
Okay, so I know there are other questions, but in the tradition of BrIAS, we are late. So that's something that I think it's an invariant of the last 4 years. So what I propose is, first of all, to thank Antonella again.
Thank you.
And to have a small pause, just 5 minutes to grab a coffee, and then we will come back here for the second seminar of today. So also for those who follow us online, you can have your coffee and we will be back soon.